So if we're going to do organic chemistry, we should start with what is organic chemistry. All right, organic chemistry is the study of compounds that contain carbon. The word organic means containing carbon. So any compound that contains carbon is considered an organic compound. Carbon has unique abilities to do things. It behaves uniquely, so therefore its compounds are very unique. Carbon can form very strong single bonds with itself, which allows large chains to form, which could allow for a huge variety of properties in our carbon compounds. Okay. So what we're going to look at, and these are, Lewis symbols and stuff again that we talked about, but what we're really going to focus on here is essentially covalent bonds. Okay, we're going to focus on covalent bonds. Let me do here. Yep, covalent bonds right here. Carbon's not going to make ionic bonds. Carbon's not going to make metallic bonds. I'm not even going to discuss them. We're going to focus on essentially covalent bonds where we're going to share electrons between two or more atoms. Okay. So in order to do that, we have to understand how many electrons carbon has the ability of sharing. Okay. So that's where we are essentially going to start. Okay. So from our Gen Chem world, I guess you would say, we know that since carbon is, or at least we should know, and if we don't blame the messenger. Write to your Gen Chem professor and say, what the heck were we doing? All right, but what we should know is that carbon, since it's in group 14 or 4A, carbon has 4 valence electrons. Carbon has 4 electrons that are in its outermost level. So carbon, all right, Lewis structure, or Lewis dot symbol, appears like this. Okay, so carbon has 4 electrons readily available to make bonds. Now, here's the deal with carbon. That means carbon can make 4 bonds. Carbon can make 4 bonds. Carbon wants to make 4 bonds. And if carbon doesn't make 4 bonds, carbon is not happy. Okay? Carbon is kind of ticked off. Carbon wants to be left alone. How it appears on the periodic table, and again, if we don't remember electron configuration, carbon looks like this. Okay? 2s2, 2p2. Here's carbon's 4 electrons that it wants to use to bond. Carbon wants to be left like that, or it wants to bond. One or the other. It wants to be left as carbon, or it wants to look like the noble gas that's coming up and fill in all those empty spaces in the 2p and form electronically, or look electronically like neon. So what we're trying to follow is that octet rule. Well, since carbon has essentially those 4 available electrons, it can make up to 4 bonds. Now, those 4 bonds could be 4 single bonds individually bonded to 4 different things, 4 of the same things, however you want to look at it. Okay? So this is carbon's strong point. Carbon's strong point is not only, and here's another strong point. Since carbon is 4 away from either looking like, and this is helium down here, and it could give up essentially these 4 and look like helium, or it can gain 4 and look like neon over here. Carbon can go either way. It can give up the 4, it can gain the 4. It wants to bond. So carbon could be strong and make bonds with all different carbons. And we show those covalent bonds, those sharings, as lines like so. The simplest organic compound out there is methane, which is a carbon that is bonded 4 times to 4 different hydrogens. But carbon also has the innate ability of making double bonds using its electrons, still making 4 bonds with oxygen. You should have seen these in Gen Chem 1 when you were doing, or Gen Chem 2, depending on where your Gen Chem 1 cut off, when you did Lewis structures. Okay. In cyanide, it can make a triple bond. So here's hydrocyanic acid. All right. Carbon still making the 4 bonds. It can make a triple bond. It can make a double and 2 singles. All right. The key is carbon can do a variety of things. What carbon can't do, and the math won't allow it, is make a quadruple bond. This can't happen. But double bonds, triple bonds, single bonds can all happen with carbon, and that's what makes carbon very unique. Carbon is so important, you are taking this course. Okay? There is 2, actually, if you go into and want to be a chem major, there's 3 courses of organic. There's Organic 1, Organic 2, and Organic 3, which is also known as mechanistic organic chemistry. So carbon-based molecules are so important to understanding not only chemistry, but those of you that are biology majors and pharmacy majors and biochem majors, the carbon molecules are so important that they dedicate at least 2 semesters and maybe even a 3rd semester to it. There's no other element on the periodic table that they're going to dedicate a science to. There is no aluminum chemistry. Okay, if you're going to take a metallic chemistry course, you're going to take a metallic chemistry course, and they're going to group all the metals in it. If you're going to take another course that doesn't deal with carbon, it's called inorganic chemistry. And essentially, when I was at the University of Scranton, the professor would, we had a light-up board, periodic table. They would shut carbon off and say, we're going to learn about everything else except carbon. So carbon is so important that not only do they dedicate 1 class to it, but 2 semesters worth of classes to it. So carbon wants to make 4 bonds. That's carbon's goal. Okay, make 4 bonds, make everything happy. All right, let's look like neon. Let's look like the noble gas that's coming up. Now in the slides, okay, I still talked about, I used the slides for the first set of slides, I used the slides from my inorganic chemistry course, general chemistry course, and I talk about ionic bonds and things like that just as a review, but we really don't need to get into those because carbon's not going to do that. Now, carbon's going to do sharing. That is the covalent bond, okay? So, we're going to erase these here, and we're going to stick with carbon, and we're going to show carbon. We're going to do all this fun stuff with carbon, and carbon does covalent bonding, okay? A little side note, the hashtag for my wedding was this. So when I told you guys I was a nerd on Tuesday, I meant I am a nerd. So the hashtag for my wedding was covalent. All right, so yeah, I embrace the nerdness. It's okay to be smart. Now, 2 types of sharing that can occur. Okay? One is when we have 2 atoms, okay, of the same nature. Another one is if we have atoms, okay, of a different kind bonding to one another. All right. So if they're bonding to one another and they're the same. Now, on my periodic table, there's a term known as electronegativity. Yeah, if you Facebook that hashtag, you'll see pictures of my wedding. Do we remember what electronegativity is? Just the general definition of what electronegativity is? Yeah, an element that wants the shared electrons more. Okay, an element that wants the shared electrons more is exactly what it is. Okay. So if we look on our PowerPoint of electronegativity, for my main group elements, okay, now my main groups again are 1, 2, 13 through 18, or if you're old school like me, 1A, 2A, and then 3 through 8A, okay, but for electronegativity, it's the want or desire for shared electrons. So for my main group elements here, electronegativity increases as I move across and increases as I move upward. Now my transition metals, they're a little weird on that. So this again is for my main group elements. So carbon is sitting right here and is a very electronegative atom. The most electronegative is fluorine, but carbon ranks up there pretty high. So carbon's going to win that tug of war for those shared electrons more often than not what it's bonded with. The only time it's really going to struggle and lose is if it's bonded to one of the higher up halogens, nitrogen or oxygen. Okay. Now, if my differences in electronegativity are 0 or close to 0, then we share what is known as, or we create what is known as a non-polar covalent bond. Okay. N2, Br2, all your diatomics, H2, O2, a carbon-to-carbon bond is a non-polar covalent bond. You are in a tug-of-war against yourself. If you're in a tug-of-war against yourself for shared electrons, no one's really going to win there. Okay? No one's going to win that tug-of-war for shared electrons. You're pretty much stuck. You're pretty much pulling with the same force. You could literally sit there and calculate electronegativity values to figure out whether you're non-polar covalent or polar covalent. I'm not going to make you do that. I just need you to know what's the difference between a non-polar covalent bond and a polar covalent. Because when we hear the word sharing, we think about it being, equal 50-50 down the middle. I'm going to share this sandwich with you. You're going to get half. I'm going to get half. It doesn't work that way. Hence, #covalent bond for my wedding. You learn that I'm not in a non-polar covalent situation. I'm in more of a polar covalent where whatever I get goes over to the wife. As she's listening outside the door, I'm going to come in and hit me with a spoon or something. Okay? But in a polar covalent bond, there's an unequal sharing. Oxygen versus chlorine, oxygen versus sulfur, nitrogen versus chlorine, carbon versus hydrogen, carbon versus fluorine. If you look at the table of electronegativity differences, there is a value that's different. So how do you decide? How do I decide whether a bond is covalent or ionic or metallic or what? If my difference in electronegativities is less than 2, I'm most likely going to be some sort of covalent bond. And if it's greater than 2, then I'm going to be an ionic bond. Well, carbon isn't really going to make ionic bonds. It's really going to focus on covalent bonds and differences of, I'm not saying it's never going to make an ionic bond, but most likely in certain situations you could force carbon to do weird things, but it's going to form covalent bonds. The question is it equal sharing or unequal sharing, and how did we distinguish between the two? Well, if nobody's winning the tug of war, we have a non-polar covalent bond. Non-polar. If there is a difference, we have a polar covalent bond. How do we show that difference? We show it with an arrow going from the less electronegative to the more electronegative. And we draw a little line to show like a plus sign, leaving the less electronegative atom. We then mark it with a lowercase delta that kind of looks like a uppercase L cursive. And the side that gets the electrons gets a partial negative charge. And the side that's losing gets a partial positive charge. Okay. So if we go back to our slides, and I go to the previous slide, In our case here, chlorine and oxygen, or oxygen and sulfur, or nitrogen and chlorine, and we go back to, discard, and we go back to here, and we look, okay, oxygen versus chlorine. Oxygen's 3.5, chlorine's a 3. All right, so oxygen's going to pull those electrons slightly more than chlorine. Oxygen should have a partial negative charge, while chlorine has a little bit of a partial positive charge, very tiny. Carbon versus hydrogen. Not that great of a difference, but carbon is more electronegative. Carbon's going to take on the partial negative, while hydrogen takes on the partial positive. Okay. Now, the truth of the matter is this. In reality, when chemists really look at the bonds, neither of them are 100% covalent or 100% ionic. They're really a mixture. Now, one might be more than the other, but they're really a mixture, and it really does fall around the electronegativity amounts that are occurring. Okay. So how about dipole moments? Okay, a dipole moment means that there's going to be a shift on one side or the other of a difference in charge. So on opposite sides of a line or distance between something, if there's a difference in charge, then we have a dipole moment. Not all molecules have dipole moments, even if they are making polar covalent bonds. So the first thing I need to have a dipole moment is to make a polar covalent bond. I need a difference in electronegativity. I need something to be positive. I need something to be negative. The next thing I need to do is make sure that across a distance, there's a quantitative value across a vector of a difference in positive and negative charges. If I am a non-polar covalent bond, I will not have a dipole moment. If I'm a polar covalent bond, it's possible I have a dipole moment, but not necessary. So we need to know how to draw our Lewis structures. Now, you should be able to do this by now. And however you were taught it, it's fine with me, as long as you could draw a proper Lewis structure. Okay. I'm going to teach you the way that I do it as a review. But again, as long as you know how to draw a proper Lewis structure, I'm okay. I have the steps on the slides the way I teach it, the way I learned it. I actually taught it myself to figure it all out, because this is a part in Gen Chem a long, long time ago. Oh, if we talk high school, we're talking 22 years ago. We're talking college, we're talking 20 years ago, which just made me feel very sad. But first thing is, you have a molecule, let's say it's CH4. You add up the valence electrons based on the periodic table. Carbon is 4 of them, plus 1 times 4 for the hydrogen, a total of 8 valence electrons. Okay. Place your most electronegative atom, or the one that's closest to the center, in the middle, which would be carbon. Place the others around it. That's step 2. And step 3 is connect them. So add up your electrons, find your central atom, place the others around it. Each line represents 8 electrons. You've got 8 electrons there, 2, 4, 6, 8. Therefore, we have our structure, or what we think of this organic compound. In order to check it, you do the formal charge. Okay, and we want our formal charge on our atoms to be 0. All right. Formal charge, if you don't remember, okay, is essentially valence electrons on the central atom. Okay, that's based on the periodic table minus what you assign to it. Okay, so it's valence electrons from the periodic table minus, and it's the valence electrons assigned, which is essentially 1/2 my bonding plus my non-bonding. So what I mean by that is, if we look at the formal charge of carbon, carbon on the periodic table should have 4 electrons since it's in group 14. I'm going to subtract that from how many bonding does it have? 2, 4, 6, 8. 1/2 of 8. No non-bonding, 0. 4 minus 4, the formal charge is 0. And that's what we're shooting for. We want the formal charge on our central atom to be 0, if possible. Hydrogen's formal charge on hydrogen. Group 1. Now I do this separate. Each hydrogen's the same. So I do it as separate and then apply it to the rest. Maybe your professor said all these hydrogens are 4 and do it that way. To me, that's more math than necessary. I look at one hydrogen, say they're all the same hydrogens, and therefore I do 1/2 of 2 plus 0 to keep my number small, and the formal charge on hydrogen is 0. Do we remember how to do this? Do I need to spend more time? I'll do a couple more examples, but do I need to spend a lot of time on drawing Lewis structures? You guys tell me. I will spend as much time, but I don't want to bore you out of your minds. Brooke, is that a no, we don't need more time, or no, I don't remember how to do it? So your no's are, we're good to go? Don't need more time? Is that what the no's are? Good. Cool beans. That means you had awesome general chemistry professors. Let's just do one more for the heck of it. Just because. We'll see how good you really are. Let's test you out then. Let's do carbonate. It's not that I don't trust you, I just don't trust anybody. Alright, so our first step is total up the number of valence electrons. How many valence electrons should we have? This is the only thing I don't like about... Well, I kind of like it because it's worse if I'm just sitting there staring at you in the classroom. The awkward silence waiting for the video to go through and you guys to type back. So questions I need answered. How many valence electrons should we start with? What's our central atom? Need more than 12. $24 sounds good to me. 24 sounds good. 4 from carbon plus 6 times 3 plus the 2 extra ones from the charge. Okay. 18 plus 4 plus 2, 24. Valence electrons. Brooke is so excited using exclamation points. All right, so carbon's our central atom. Our next thing is to draw around our outer atoms and connect them. So if we do that, we've used up 6 electrons. We're down to 8 valence electrons. 2, 4, 6 used up. We're down to 18, I should say, valence electrons. Now, if we follow the list that I gave you, or however you learned how to do it, you complete the octet around the central atom. That leaves us 16, as long as the central atom completes the octet. Complete the octet around the other atoms. All right, now if I do so, 2, 4, 6, 8, 10, 12, 14, 16, whoops, too many, 18. Okay, so we get rid of those, and we're short 2 over here. We can't just draw 2 in, and we can't just make up 2. So what do? How do we make the octet complete around here and keep the octet complete around the other ones? And how do I add a double bond to one of the oxygens? I can't just draw one in. It's got to come from somewhere. So where's it coming from? Very good. That's what you have to do there, Brendan. You're right on making the double bond. We got to make it. Now, here's the key to organic chemistry. If you only learn one thing from me in this whole entire lecture series, the arrow always goes from the electrons to where it's going. You don't erase the dots on them, Madison. Ugh. Move them, move them. Use the word move them. Transfer them. Now everybody's got the octet. Everything's completed. If we do the formal charge, my formal charge should add up to be a -2. Hopefully it is. Now these oxygens are the same. I'm going to put little stars next to them. These are the same, and that oxygen's different. So we have 3 formal charges. 1 for carbon, 1 for each of these oxygens. All right, they're the same, and 1 for this oxygen here. So the formal charge for carbon is going to be 4 minus 1/2 of 8, 1/2 of its bonding, plus its non-bonding. It has no lone pairs, 0. So 4 minus 4, 0 for carbon. That's good. Let's do double bonded oxygen, okay? Formal charge on oxygen that's double bonded. We won't put a star next to it. 6 minus 1/2 of its bonding. Has 4 bonding. Plus its non-bonding, 4. 6. So this will be 6 minus 6, 0. And then the formal charge for oxygen star. 6 minus 1/2 of 2. Okay. Plus 6 non-bonding. So it has 2 bonding, 6 non-bonding. That's a -1. So each of these are my negatives. Okay. Questions on that? You didn't have to retract your message and delete it, Madison. It's all right. Everybody breathe. I told you from day one I am very sarcastic. And we're only on day 2 here. Relax. It's okay to be wrong. I'm going to make mistakes. We're all going to make mistakes. It's all good. I'm putting it back up there. All right, my question to you. I know these are both CO2. I know they both act like CO2. My question to you is, okay, is each oxygen seeing the same bonding on both sides here? So if I were to tell you label oxygen A over here, would oxygen A be the left, the top, or the right? So essentially, did we just turn this molecule this way? Turned it 1 turn, so now A is here, C is here, and B is there? Or more like something like that, maybe even. A is here, C is there, and B stays up on top. Or did something else happen? Well, in reality, this is still A, this is still B, and this is now C. And what happens is, there you go. Yes, Keith. And why do resonance structures exist? Well, the first thing is, what is a resonance structure? A resonance structure the key to that is it's going to keep the same energy by shifting the electrons around. And again, I'm giving you a down and dirty, short summary of resonance. So what's really happening in our case here is the following. Okay, let's do this. From here to here, from here to here, from here into there. Okay? The electrons are constantly moving. It's not just twisting around and moving in space. The electrons are constantly moving and forming a resonance. Yes, you guys are right, forming a resonance. Okay. And when I do this in my Gen Chem class, I get a whole bunch of kids looking at me and saying, like, that's bullshit. This just basically flipped over and you're lying to us. It's just rotating in space like this. You know? And it's not, and they actually proved that it's not. They actually proved that the electrons are moving, and here's how they did it. If you take a molecule, it doesn't matter, and in the slides the molecule example is ozone, but it doesn't matter. If we were to use a radioisotope of oxygen, something that's a little bit heavier, oxygen 18 instead of oxygen 16, where we can follow it. Okay? And we can mark oxygen 18 and we can figure everything out. And we said, okay, oxygen 18 is double bonded here, and it's also double bonded there, and this just rotated like this. If we were to look at the bond angle or bond length, even more specifically, of the carbon to oxygen bond here, this length should not change. It should be the length of a carbon to oxygen double bond. If this oxygen is never changing, then this length should never change. So when we track this radioactive A, its bond length should be the same. The problem is when they did that with ozone and they looked at the bond lengths and they did that with these kind of molecules and looked at the bond length between each oxygen in, let's say, ozone or in carbonate or in whatever, CO2, all right, well, now CO2 wouldn't work. But in carbonate or sulfate or nitrate, anything that has double and single bonded oxygen in the same molecule, okay, they found that the bond length was somewhere between a single bond length and a double bond length. There was an average between, which means that this bond length is constantly somewhere in between being a double and single bond. Well, what does that mean? Well, since the electrons are constantly moving, and we know that bond length, okay, is, directly related to how many bonds we're making. The more bonds we make, the shorter the length. A single bond is longer than a double bond, and a double bond is even, or a triple bond is even shorter than a double bond. Well, if we're somewhere in between a single and a double bond, that means we're going back and forth in between this whole time because the electrons are constantly moving. Okay. And since the electrons are constantly moving, all right, then we have these resonance structures. Now, the key about resonance structures is we're going to try to keep the same amount of energy we can if they're going to be similar, and we're going to be able to move the electrons. The big thing I always tell people, don't get resonance happy, meaning you have to draw 1 million resonance structures. And number 2, you can't draw them if there's no free electrons moving around. I.e., there has to be a double bond or lone pair. You can't take these here and move them. Foreshadowing, you might be able to. But for right now, we can't. These are making up the skeletal structure. They're not going to move. Foreshadowing, take that with a grain of salt down the road. Okay? So questions on resonance and Lewis structures and figuring out the proper structure for carbon and stuff like that, because there's the first question or some of the questions you're going to see on the exam. How many resonance structures do you expect, or things like that? What's the formal charge on carbon? What's the formal charge on one of the oxygens? What's my central atom? How many total valence electrons should there be? Things like that. All right, if we have nothing, then I'm going to move on. If you have something, stop me now, or stop me, or email me, or whatever. Good. Hopefully it's a review. Hopefully I'm cleaning out the cobwebs and stuff is coming back. So what we drew on the board is 2D structure. 2D structure is great. It's fantastic. It helps us out. It lets us see things, but it's irrelevant in our chemistry. I mean, it helps and it shows what our bond is, but what's relevant in biochemistry and drug interactions and our sense of smell and vision is, what does the 3D structure look like? Yes, it's important to know the 2D because we got to be able to take that 2D structure and turn it into 3D molecular shapes. Now, we're not going to get into drawing the 3D structures yet and how they're going to look and dashes and wedges just yet, but we should be able to take our 2D, and what we're going to talk about now is Vespert theory, and again, make them into 3D structures. So carbon tetrachloride, which is a carbon that is bonded to 4 chlorines. Okay. Wow, that's a good one. And that's no good. That is gone. We're on fire right now. Keep lighting it up. All right, get this blue here. All right, carbon tetrachloride, or methane for that matter. If we draw out the 2D structure, we draw out the Lewis structure, we do everything, we get the correct formal charges. Carbon tetrachloride should look like this. But in reality, so if we were to look at this, this looks like it's a cross. This looks like it has 90-degree angles all around it. But in reality, the bond angle between here, here, and here is really 109.5. And the reason being is that the electrons are repelling each other. And since the electrons are repelling each other, they're causing instability. So our molecules stretch those out as far as they possibly can without putting extra strain on the central atom. So in reality, the carbon tetrachloride bond angle is 109.5 because what it forms is not a cross but a tetrahedron. Now, a tetrahedron is an object that has 4 faces and 4 vertices, and each face is an equilateral triangle. Methane does this, carbon tetrachloride does this. Okay. Any of your carbon that contains all single bonds does this. And this is what blows my mind about chemistry and all of that fun stuff. Carbon really narrows itself down to 3 molecular shapes. Carbon could be linear, carbon could be trigonal planar, or make a triangle in the plane essentially, or it could be this tetrahedron. And carbon does it basically knowing what it's bonding to. So carbon says, hey, there's 4 hydrogens here, I'm going to make methane, I'm going to make a tetrahedron. But it could also sit there and say, okay, I'm bonded to oxygen. So I'm going to be linear, and I'm going to make CO2. Actually, there's more oxygen there. I'm going to make the carbonate anion, and I'm going to be trigonal planar. Like, carbon knows, and I know the word knows and knowledge is a human thing. But that's the beauty of this. Everyone looks at this chemistry stuff and looks at organic, and you hear the horror stories of organic, and oh my God, it's a terrible course, and it's so hard, and it's a weeder out, and everyone fails, or go take it somewhere else, or, you know, you're going to have to take it 3 times, or blah, 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 and you talk to anybody in the medical, I hate organic. Listen, organic is awesome. And I'm a biochemist, and I was a biology major, and I really didn't come around to organic until grad school when I had to take a mechanistic course. And to be 100% honest, I got a C in it in grad school. Everybody thinks every professor got A's their entire life. No. It was one of the hardest courses I've ever taken in my life. Okay? I was so proud of my C. Like, I was like doing dances down the hall. Okay? But it doesn't have to be like that. Stop thinking of it as a course and start thinking of it as life, because that's what it is. So it's crazy to think about. Carbon is there, and now I got to kind of look at you here. Carbon is sitting there, and carbon is saying, well, I have oxygen available, and I just know that I have to go linear to make CO2, but if I want to make carbonate, I got to go trigonal planar. Actually, I'm going to go bond with hydrogen, and I know I'm going to have to make a tetrahedron, and I have to do it because the math says so, but I have to do it because I need the electrons to spread out, and I just know to do it because that's the way it has to be, or I'll be unstable, and there'll be, all right, compounds and electrons and everything flying off and bonds breaking and instability and chaos. So in order to bond and in order to make carbon tetrachloride, well, I have to be 109.5. But if I want to make CO2, well, I better be 180 degrees and be a straight line. And carbon just knows to do this. So what I tell my class all the time is, and I don't mean this in a bad sense, but we're all insignificant. We don't matter. Carbon doesn't care where the carbon comes from. It's just carbon. We are just carbon and oxygen and chlorine and bromine and fluorines that are floating around. Not us personally, but just what's around us. We're carbon, oxygen, nitrogen, some sulfur, some phosphorus. Okay, a bag of, transition metals and some metals sitting in there. And we're in this form for this time being. And whatever you do in this form with your carbon in this time being is your call. But when you're dead and you're gone and everything's over, your carbon's going to go back out and it's going to find a partner and say, now I'm going to make these compounds. And it's going to continue on. And the carbon that made you up or makes you up now was always here. It was here since the first carbon molecule formed. And carbon's been doing this forever, knowing that this is how it needs to do the things it does in order to make the compounds that we need for biological life or for whatever it is. So at night, when you can't sleep, think about that and see if you can sleep, because you probably can't sleep. Now, there's a thing out there now where people are saying that the atoms have atomic memory and things like that, that they just do this because they know, again, I'm using knowledge, but they know that this is the right way to do it. Okay. So the chemicals that are making you up have always been here. The carbon that's been making you up has always been here. What you're going to explore in this course and all your biology courses and your organic courses and things like that is what you're doing with that while you're here. You're understanding what makes you up. Yes, is it going to be challenging? Yes, is there going to be tough concepts? Yes, are you going to be stressed? Sure, I'm not going to lie to you. It only gets harder and harder. Trust me on this. Okay? But by building a foundation and by you expanding your mind and applying it, that's going to be the key. Looking at the brilliance of what's going on around you is crazy. Think about it. You inhale oxygen. That goes through a bunch of metabolic processes that you're going to learn in biochem, which comes from your basis of organic chem. The byproducts of those biological processes are CO2, our garbage. Okay? That CO2 is exhaled. The trees take it. They do their biological processes and turn it into their waste, which is O2, which we need to turn into waste, which is CO2, to make their biological processes, and so on and so forth. Here, I'll pass it over to you guys so you can understand what's going on here. Right? Like, it's mind-blowing that carbon, something this fantastic, something this irrelevant, something this small, carries such a strong impact. So don't freak out. That's my key. Start applying it. Start realizing. Start looking around. Start observing. Okay? Start seeing things from a different angle. Don't put all your classes in little components. Apply it across everything. Your carbon is now sitting in you for the next 80 to 100 years, whatever it is. But that carbon is doing things, switching, moving, changing, having resonance structures, moving electrons around, finding the correct shape to have the Vesper theory so that you can exist the way you're existing. It's crazy. All that's going on. So when I say that we're insignificant in the grand scheme of things, we are. We're just a shell of the chemicals that are moving around for this instance. Yes, you matter in life, and yes, you matter to people, and don't get me wrong on that. But in the grand scheme of things, universe doesn't really care. All right, now off the depressing part of the universe not really caring and carbon not caring, we have our molecular shapes. Okay? Facts. All right, so with our molecular shapes, we got three main molecular shapes that we're going to focus. Carbon is going to be utilizing. And here's the big three for carbon. And since we're talking about carbon and we're not talking about anything else, okay, we're going to focus on these big three. Right there. Linear, trigonal planar, and tetrahedral. It all comes down to how many domains do I have? And by domains, I mean areas of electrons, whether they be lone pair or whether they be bonded electrons. So, we only focus around our central atom. We look for locations, we'll find electrons. Bonding electrons count as one domain. Whether they're double bonds, triple bonds, or single bonds, they're one domain. So this down here has two domains. These up here, this carbon has four domains. CO2, carbonate is what I was trying to say there. Okay. Carbonate has three domains. 1, 2, and the double bond counts as 3. 3 domains. Okay? Tetrahedral, linear, 3 domains, trigonal planar. We don't have to worry about bent anymore. We don't have to worry about any of that you learn in Gen Chem, because we're not going to talk about water, and we're not going to talk about nitrogen as a central atom, and we're not going to talk about, not that they're not going to be in our molecules, but we're really going to focus on just carbon. So we just have to really worry about these 3 right here. Okay. And that's all. Okay. We don't have to worry about these over here as our molecular geometries, because it's going to be rare that carbon has a lone pair on it. Does that mean carbon won't ever have a lone pair? No, carbon might have a lone pair. It might take this trigonal pyramidal shape for a little bit, but it's not going to like it, and it's going to go to tetrahedral as fast as possible. So we really just have to focus on linear, trigonal, planar, and tetrahedral. Okay. Again, I'm using my Gen Chem slides for this beginning, so you're going to get a little bit more than what you were expecting, all right, or what we need to talk about. Bond angles we talked about. Double bonds are going to change the angles. A tetrahedron, all right, is 109.5. Trigonal planar should be 120 all the way around. Double bond's going to push more, causing the bond angle to be bigger from the double bond to the single, and the singles to be smaller. More electrons, more repulsion. All right, we don't have to worry about octahedral and stuff like that. What if we get a crazy molecule like this and we start building our chains? What would our geometries be then? Well, there's 3 geometries. Each central carbon has a geometry, and not only that, does oxygen also have one. So if I have multiple carbons, I'll have multiple geometries. So this carbon here would be tetrahedral, this carbon here would be trigonal planar, and oxygen over here ends up being tetrahedral bent, but we're really only going to focus on the carbons. Okay. Molecular shape is going to play a role on whether I have a dipole moment or not. Okay. And here's where the importance comes into play, guys. Okay. I need, in order to figure out if I have a dipole moment. Now, carbon and chlorine. Chlorine's winning that tug of war. Chlorine should be the more electronegative. Carbon's going to lose. However, this is a no dipole moment. Okay. How do I know? Okay. Draw the Lewis structure the way you see it. How many lines of symmetry do I have? How many different ways? We're on a roll here. How many different ways can I cut this and have a line of symmetry? Okay, so if I have methane, carbon is winning the tug of war. All right, carbon's winning the tug of war against every hydrogen. All right, but there is no dipole moment. There is no dipole moment because I have 2 lines of symmetry. However, if I change that and put it as this, now I only have 1 line of symmetry right here. This does have a dipole moment, and it's going towards the chlorine. This one has no dipole moment. If I have 0 or 1 line of symmetry in my molecule when I draw it, then I'll have a dipole moment. If there are 2 or more lines of symmetry, I don't have a dipole moment. The only other option is you to draw vectors and the lines that are intersecting the vectors. And this way, to me, is a lot easier than getting into vectors and all that fun stuff. So if we look at some examples, H versus Cl, polar dipole moment, yes. Carbon tetrachloride, no. Lines of symmetry here and here. Ammonia would. BF3 would not. And like I showed you here on the slide, definitely would. Okay, or on the board, I should say. All right, so that ends our first part of Chapter 1, and I'm hoping it was a review. You could start looking through Chapter 1. Okay, and look for problems with that. If you do need more problems or something like that, just feel free to email me. I can give you more problems. But just looking through Chapter 1 on molecular shape, polarity, dipole moments would be the homework.